Have you ever dropped something? A pen? A book? Or your keys? Of course you have. You watch it fall. And you think it's gravity. For centuries, we have thought of gravity as an invisible rope, a mysterious force that pulls things down. Sir Isaac Newton gave us the math for it. And it worked beautifully. It let us predict the paths of planets. But the why question remained a puzzle. Why does an apple fall toward the earth? Why does the moon stay locked in orbit? A young patent clerk had a wild imagination above gravity. Albert Einstein came along and told us a completely different story. A new story of gravity. It's not a story of pulling, but it's a story of bending. A story where the stage of the universe itself is an active player in the cosmos. This new story of gravity is now known as the general theory of relativity, and it completely reshaped our understanding of the universe. To understand Einstein's gravity, we need to upgrade our vocabulary and our imagination. We tend to think of space and time as two totally separate things. Space is the three-dimensional arena: length, width, height. You can move forward, backward, left, right, up and down. Time, on the other hand, is the relentless ticking of a clock that moves us from the past, through the present, and into the future. It's a one-way street. For most of human history, these two concepts were kept in different sections. Space was the stage, time was the script. Einstein realized that this separation is an illusion. Space and time are not separate. He stitched them together into one four-dimensional fabric space-time. Think of it this way: to schedule a meeting with a friend, you need four pieces of information. You need a location in space, say the corner of 5th Avenue and 42nd Street on the 10th floor. That's 3 dimensions. But you also need a fourth piece of information, a time, like 3 o'clock PM. Without the time, the location is useless. Without the location, the time is meaningless. Every event in the universe, from a supernova explosion to you sipping your coffee, has a unique address in space-time. Now that we have our four-dimensional fabric of space-time, what happens when we put something on it? This is where Einstein's idea gets really fun. Imagine space-time is a giant, taut rubber sheet or a cosmic trampoline stretched perfectly flat in an empty universe. With nothing on it, the surface is smooth. A tiny marble rolled across this flat sheet would travel in a perfectly straight line forever and ever. This represents an object moving through empty space far from any source of gravity. It follows a straight path because there's nothing to change its course. It's a simple, predictable, and somewhat boring universe. But our universe isn't empty. It's filled with stuff, planets, stars, galaxies, and even you. In Einstein's view, all of this stuff, all this mass and energy, doesn't just sit in space-time. It interacts with it. It tells space-time how to curve. Now, place a heavy bowling ball in the center. The sheet sags. The bowling ball creates a deep, curved depression in the fabric. The heavier the object, the deeper the dent it makes. This is the essence of general relativity. Mass and energy warp the geometry of space-time around them. In Einstein's world, this curvature is gravity. Gravity is the geometry of the cosmos. So, we have a warped, dimpled cosmic trampoline. Now what? Let's roll a small marble, our test particle, not directly at the bowling ball, but near it, across the curved part of the sheet. The marble will try to move in a straight line, but it can't. It's rolling on a curved surface. As it approaches the bowling ball's depression, its path will bend. But if you were a tiny ant riding on the marble, you'd feel like you were going perfectly straight along the landscape available to you. This is exactly how Einstein explained the motion of objects in a gravitational field. Planets, comets, spacecraft aren't being pulled by the sunbeam. Instead, they are simply following the straightest possible path through the curved space-time that the sun has created. This straightest possible path on a curved surface has a special name, a geodesic. Your car driving down a highway follows the geodesic of the road. An airplane flying from New York to Tokyo follows a great circle route. A geodesic on the curved surface of the Earth, which looks like a long arc on a flat map but is the shortest possible path. The Earth's orbit around the Sun is a geodesic, but in the language of four-dimensional space-time, Earth is just coasting. It's following its natural, straightest path through a cosmic landscape that has been warped by the Sun's immense mass. The Moon does the same thing, following a geodesic in the smaller space-time dimple created by the Earth. There is no mysterious force. There is only matter following the contours of the universe, like a train following its tracks. Even light, which has no mass, must obey a geodesic. An idea as radical as general relativity needs some serious proof. One of the first triumphs came from our own solar system. Mercury puzzled astronomers for decades. Its orbit wobbled, it precessed. Newton couldn't fully account for that extra wobble. Einstein calculated Mercury's orbit with general relativity. The numbers matched. The extra wobble. Mercury moving deep within the Sun's steep spacetime curve. Then came the famous test of 1919. Eddington's expedition photographed a solar eclipse, and the star field around the Sunday comparing eclipse plates to earlier images showed the stars had shifted. The Sun had bent the light exactly as Einstein predicted. Einstein became an international celebrity. Gravitational lensing, dramatic light bending across the cosmos. Massive galaxies, galaxy clusters act like giant cosmic telescopes, bending and magnifying background light. Sometimes that creates multiple images or ghostly arcs. Astronomers use lensing to map invisible dark matter and to study the earliest galaxies. Perhaps the most extreme test, black holes. In 2019, the Event Horizon Telescope imaged the supermassive black hole in M87, a dark center ringed by light bent into a circle. So, Einstein's vision of gravity as curved spacetime is a beautiful theory that explains Mercury and black holes. But it also guides the global positioning system. Satellites with atomic clocks in weaker gravity tick faster than clocks on the ground. They gain about 38 microseconds every day. Without correction, your position would drift by about 7 miles per day. In 2015, scientists at LIGO made the first direct detection of gravitational waves, ripples, in the fabric of spacetime itself. They came from two massive black holes that spiraled into each other a billion years ago. A shudder through spacetime raced across the cosmos at the speed of light. By the time it reached us, it was faint, but our detectors felt it. We have now heard echoes of dozens of cosmic collisions. Ultimately, this is why the story of gravity matters. It's not just about a better formula. It's about a deeper understanding of our place in the cosmos. It tells us the universe is a dynamic, interconnected whole. The key idea to hold on to is this: mass tells spacetime how to curve, and curved spacetime tells mass how to move. Think of the universe not as a stage, but as a dynamic dance floor, where the dancers and the floor shape each other with every step. That is what gravity really is. Next time something falls, remember, it's following the straightest path through a curved universe, and we're all living inside its gentle, persistent curves. Thank you for watching the whole video. Please like, share and subscribe Space Science, and also make sure to leave comments. It really helps me to get motivated.